Hello and welcome to the channel Understanding.Concepts.Of.Physics. So finally we have reached where the oscillation chapter ends. This is the last topic for oscillation, that is the magnet vibrating in a uniform magnetic field. After this we are going to start with the numericals of oscillations, and the theoretical part, all the conceptual part, I have made it sure that you have understood. There might be few topics which you just go into detail to find out further corollaries and newer theorems as well, but depending upon your board, in which board you are, just realize what is required and what is not. So let's see, magnet vibrating in a uniform magnetic field, how are we going to solve this? So I am assuming that there is this magnetic field which is going from the bottom to the top. So this is the magnetic field, which is orange colored line, and right now I am marking it with a laser. It is going from the bottom to the top. So basically we can say there is a very strong north pole at the end and a very strong south pole at the end on the top, because magnetic field always goes from the north pole to the south pole, and it's a uniform magnetic field. So if you see, the spacing between them are equal, and also the length is also the same. Then we have placed a yellow colored bar magnet over here, whose north pole is at this point and the south pole is at this point, and this is the axis of our bar magnet, which is actually making an angle of theta with the magnetic field. Now because of this thing, north pole, because this is a very strong north pole and this is a very strong south pole, north pole is going to get attracted towards south pole and the south pole is getting attracted towards the north pole. This magnet is going to get twisted, it will going to get rotated, and it will rotate and it will try to align itself over here, but it is not going to stay at this point, it is slightly going to go on the other side. Now at this point again, the forces will act upwards and downwards, and it will act upon a torque, and it will again try to balance it in the center, but it is not going to stop at the center, it is going to go on the other side, and again it will go to the other side, and again it will go to the other side. So the magnet is just going on to oscillate like this, back and forth, back and forth, back and forth. So this oscillation, the time period of such oscillation is how much we are supposed to derive it today. So here what we need is, we will be needing a formula, which is the formula for couple, or we also call as torque. Now couple or torque, the formula in magnetism is torque or couple is equal to magnetic moment into the magnetic field. Now I'm sure that couple and torque are two different things. So whoever are physically inclined, or if a physics teacher is watching, then yes, couple and torque, there is a difference to both of them, but right now we are not discussing the difference between them. The formula for torque and couple is equal to M cross B. Now here M stands for magnetic moment and B stands for external magnetic field, the strength of external magnetic field. Now this formula comes in magnetism, and right now I am not discussing how this formula comes. We are only here to discuss the time period of an oscillating magnetic needle. So just follow up this formula as of right now. So tau is torque, M is magnetic moment. This is that quantity which makes a magnet and a non-magnet a non-magnet. And there is a cross product, and all three are vector quantities. Magnetic moment is measured in Tesla, and magnetic field is measured in Teslas, and magnetic moment is measured in ampere meter square. Okay, current into area. So if you remember the product formula for cross product, it is torque is equal to, just the basic formula is A cross B. So like if there is a quantity like A cross B, and if you wish to solve it, the cross product formula is A B sine theta. So wherever A cross B is there, you can write A B sine theta. So if I got an M cross B, I can write as M B sine theta. Now as theta is tending to 0, because when it is going to oscillate here back and forth, when the magnetic needle is going to oscillate, it's not going to oscillate to a very big angle, it is going to oscillate with a very small angle. So theta is very near to 0, and if theta is very near to 0, we can write as sine theta is approximately equal to theta. This is a mathematical identity we are using. So wherever there is a sine theta, we'll write as a theta. Now there is one important here thing for direction is, okay, your restoring torque is always in the opposite direction to the angular displacement. They both are always in the opposite direction. So tau and theta are always in the opposite direction. That's why we are using a minus sign in the equation. So whenever you try to rotate this magnet from its equilibrium position, let's say you are rotating it here, so the torque, restoring torque, is actually developed here, and the angle is towards the clockwise direction. Because this theta and because this torque are always in the opposite direction, we are going to write a minus sign over here. However, we are going to ignore that minus sign in very short time. Also, from rotational motion, we can see torque is equal to I into alpha. So wherever there is a torque, I can just replace this as I alpha. So I have put I alpha is equal to minus of mb theta. Now I want to purposefully find out theta upon alpha ka value. So theta upon alpha value is equal to, now alpha comes here and this minus mb goes on the other side. So I upon mb becomes our equation. Now here I am ignoring my minus sign, and the reason is, okay, when I am putting that in the further equation, I don't need that minus sign. Actually minus sign is just signifying that alpha and theta are in the opposite directions. Now we have derived this equation, we know this equation, we have been deriving this equation since 2 to 3 videos behind, which says t is equal to 2 pi root of theta upon alpha in angular simple harmonic motion. So if you have not followed that angular simple harmonic motion, then I would request you to go back to the playlist and watch the video on angular simple harmonic motion. So wherever there is a theta upon alpha, I can write as I upon mb. So wherever there is a theta upon alpha, I am just replacing that t is equal to 2 pi root of I upon mb. Now here you should note that I stands for, in this equation, I stands for moment of inertia. Again you go back to rotational motion, moment of inertia. Then m does not stand for mass, m stands for magnetic moment, and B stands for magnetic field. So this is very clear. Just do not get confused with m. M here is magnetic moment and not mass. I stands for moment of inertia, and the rest of the terms are have the usual meanings. So I hope you have followed this small derivation. This derivation is also there in your magnetism chapter. So if you prepare this derivation, you have also prepared this derivation from magnetic effect of electric current or maybe magnetism. So in one of the chapters this is there. So I hope you have followed. Thank you so much for watching. In case if you are still with me, subscribe the channel. In case you have not done yet, watch the videos in a series and you will follow a lot of things. Slowly and gradually, one video at a time will make you ahead a lot after a certain period of time if you follow the routine. Thank you so much. Have a nice day. Bye.